Hi folks, let's take some time to talk about the atom and the nucleus. Like what is in the atom, how is it made up, all of that sort of stuff. So first we need to mention kind of all the pieces of the nucleus. So for example, we have, or sorry, not the nucleus, the atom. We have three parts. We have the electrons, the protons, and the neutrons. And the protons and neutrons are known as collectively as nucleons because these are the part that are in the nucleus. So I think this is pretty familiar to you. The general gist of it is we have a nucleus with the protons and the neutrons, and then we have electrons in an electron cloud, we often describe it. We're not going to get too into the details of that, but what you kind of want to be thinking about is the electrons are kind of smeared out and take up space around the nucleus. So they're not flying around as discrete particles, but because we've talked about the wave-particle duality, they're kind of smeared or spread out all around the nucleus is kind of how I understand it. And the scale here is pretty crazy because the nucleus has 99.9% of the mass, so almost all of the mass. I think it might even be higher than this. But the atom, the nucleus, takes up a tiny, tiny, tiny fraction of the atom. So the atom is approximately 100,000 times bigger. 100,000 times bigger than the nucleus. So if you want to know what this means, if you had a ping pong ball as your nucleus, if that was how big the nucleus was and you wanted to scale up the atom to that size, the orbits would be, this electron cloud would be like a kilometer out from there. So the nucleus is absolutely tiny, but has almost all the mass. So it's just something to kind of be aware of as we go forward. So the electron orbits are as follows. When we look at the atom, we know that the electron, we have this thing called the emission or absorption spectra. So if we shine light on an atom, or if we give energy to an atom, then what happens is it gives off light as well. And if we track where all that light is, we might see something like the following. So you only see specific colors come off of it. And then if we want to kind of simplify that down below here into a diagram, we have the actual lines of the wavelengths of light that come off of an atom. So all this is to say there are very specific light that comes off of an atom when we excite the electrons. So if you remember back to chemistry, or if we've talked about it before, you've got a nucleus, and then it's like you've got these shells around it where electrons can sit, and they can only sit in these specific shells, and when they move between shells, they either need to gain energy to go farther out, or they need to lose energy to come closer in. And as they lose energy, they lose that energy by giving off light. As they gain energy by absorbing light. And so if we look at what colors of light or what wavelengths of light an atom absorbs or what wavelengths it gives off, that tells us how far apart these orbitals are, and that tells us they are at discrete points. And that's because we're kind of moving, again, between these ground and excited states. And so this matches well with the wave-like behavior of atoms, or of electrons. So we've talked about how electrons will be sometimes behave like particles, sometimes behave like waves. This is one of the places it behaves like a wave. And each of those levels that we talked about is where a wave can resonate. So if you remember, we talked about standing waves before, like a spring or a guitar string that vibrates, and only certain frequencies or certain wavelengths will fit. Well, we're doing the opposite of that. We're saying that the electron has a certain frequency, has a certain wavelength, and it will only fit at certain intervals. So only when, if you look in this bottom picture, only if the kind of the circumference, so to speak, is large enough to fit that wave in properly, can it resonate and exist there. If you look at the second example on the right, you'll notice that we start here. I know it's a little hard to see the yellow, but we start here, you trace that around, and you keep going, and it doesn't line up again. Whereas in this first one, if you trace that around and come back, you come back to the same spot. So this is why they have to be at certain distances, quote unquote, from the atom. And now it's much more complicated than this, but this is the basic idea. You can kind of think about it like it. Only at certain circumferences is the wave-like behavior of that electron going to fit, and that's what locks them into these levels. And then, like we said before, the difference in energy between those levels explains why we see those real discrete emission spectrum lines. We're not going to worry too much about it other than just the idea that there have to be those discrete levels, and that's because electrons behave like waves in that case. All right, let's take a bit of time here just to talk about the structure or organization of the nucleus. So the nucleus is held together by the strong nuclear force. And if you remember way back earlier in the year, I think we mentioned the 4 fundamental forces. You have gravity, you have electromagnetic force, you have the strong nuclear force, and the weak nuclear force. And any other force or interaction that we see in the universe can be simplified to actually being a bunch of atoms or a bunch of particles interacting with one of these forces. So the thing to know about the strong nuclear force is it's a very short-range force, we say. So unlike gravity or unlike the electromagnetic force, which can act over a long distance, the strong nuclear force only works for, we'll say, touching protons and neutrons. So you can think about it like Velcro. If a proton and neutron are brought together so that they touch, and touch is a weird kind of nebulous word when we get really small, but we're going to simplify and just pretend that protons and neutrons are little ping pong balls covered in Velcro. So if you have 2 of them touch, they'll stick together with the strong nuclear force. And the nuclear force is very, very, very strong. So if we have, say, 2 protons, they can stick together. If I had a 3rd proton, it can stick together. If I had a 4th proton, if you'll notice, this 4th proton that I just added, it's touching 2, but it's not touching this 3rd one. So if all these are protons, they're all positive. They're all pushing away with the electromagnetic force, but because they're being touched by a bunch of they're being held together by that Velcro, that strong nuclear force. This holds together. And this will keep going, but eventually, if I add too many extra protons, now you can see there's 5 protons pushing away this one over here, and only 2 holding it together. And the strong nuclear force is strong, but it's not strong enough to hold infinitely. So eventually, if there's too many protons, this guy gets pushed off. Or, maybe it's this bottom proton that gets pushed off. And then if they get pushed off, the force that's repelling them all gets weaker, and then they can hold together with the strong nuclear force. So the solution to make larger atoms than 3 or 4 protons is to put in some neutrons as well. So for example, I can have that same number of particles. So we'll put 6 in here, but say only half of them are protons. Now this proton is being pushed by 2 protons, but it's being held by 4 particles, 4 nucleons. And so that means that we can essentially get less push for the same amount of stickiness, because not all of these particles are not all of these nucleons are pushing away. And that's where we have this diagram to the right, which shows the stability. So when we're really small, when we're at, if you see this is the number of neutrons and the number of protons, when we have really small atoms, we need roughly equal numbers of protons and neutrons to be stable. And that's what you'll see over here. If it's this black box, it's stable. And then these other colors basically tell you how quickly the nucleus falls apart. So what you'll notice is we have this curve that we call the curve of stability. So all these black dark marks are stable. All of the dark reds and oranges are pretty stable but will eventually fall apart. All of your blues and dark blues fall apart almost instantly. They're very, very short-lived. And what you'll notice as the bigger we get, the more neutrons we need than protons. This diagonal line right here represents an equal number of protons and neutrons. And so you'll see we need more neutrons as you get bigger. And this is because, if you remember, nuclear force only acts for touching particles. The electromagnetic force acts on all the particles. So when you get to a really big nucleus, what you basically end up need to be having is each proton kind of needs to be completely surrounded with a bunch of neutrons so that we can spread out the protons. And if you remember from the electromagnetic force, the farther apart they are, the weaker the force is. So in order to have these big, 80 protons together, they need to be pretty spread out with lots of neutrons in between, just velcroed together, so that the force that is felt by an individual proton is weaker because it's far away from all the other protons. So that's a basic primer on kind of the structure of the nucleus. If you have further questions, let me know, but otherwise we'll wrap up here.